And we have the next talk, Bouakkaz and chemists, existence and uniqueness results for a nemonotropous model and variable delays and a nonlinear harvesting term.
Hello, I'm here.
Yes. I see you.
Good morning.
Yes.
Thank you, Chairman. Hello, everyone, and welcome to my presentation. First of all, special thanks to the organizers for giving me the opportunity to participate at this very interesting conference. Let me also pay tribute to all the efforts that they have made for organizing it. My name is Bouakkaz. I'm an associate professor at 20 August 1955 Skikda University from Algeria. So today I'm going to talk about existence and uniqueness results for a hematopoiesis model with variable delays and a nonlinear harvesting. My co-author in this work is Dr. Rabah Khamis, an associate professor at the same university. This presentation is organized as follows. In the beginning of it, I will present our revisited model. The aim here is not to offer a detailed biological explanation, but rather to give an idea of what the model is about and of what makes it different from its counterparts in the literature. Next, in the second part, I will use Banach and Chowdhury's fixed point theorems together with some useful properties of an obtained Green's function to establish our main results. And finally, the presentation will end with the conclusion recapitulating the guiding idea of the work. First things first, let's begin by talking about our revisited model. This work is devoted to study the following hematopoiesis model that describes the production of white blood cells in the bone marrow. This model involves two types of delays. The first one is time-varying delay, and the second delay is time and state varying delay, which gives rise to the appearance of this second iterate. The second iterate of X is the composition of X with itself. It is worth noting here that equation 1 is a special type of the class of functional differential equation with equations with delay depending on both time and state. More precisely, we can consider this first order differential equation as a mother class of equation 1. In medical terms, X of T stands for the density of mature white blood cells in blood circulation at time T. The cells are lost from circulation at a rate A of T. This term, which depends on the cell densities at the earlier times, is the white blood cell production, where P of T is the production rate, tau of T is a time-varying delay representing the transit time required to release mature cells into the circulating bloodstream. H denotes the harvesting term, which may due to blood donation, cupping therapy, or taking blood samples, for example. Tau sub 1, which describes the time delay between the production of immature cells in the bone marrow and their maturation for release in circulating bloodstream, depends on both the time and the current density of mature cells. This dependence results from the fact that some growth factors and hormones control the division of the hematopoietic stem cells. Indeed, when the number of mature blood cells is large, some growth factors and hormones suppress the division of the hematopoietic stem cells, and in the converse case, it will be promoted. To recap, we revisited the classical Mackay glass model according to the fact that several studies revealed that the delays in real phenomena are generally dependent on both the state and time, and which usually cannot be set aside or ignored, especially in medical and biological sciences. Harvesting blood cells, which reduces the population or the cell population, plays an important role in the cell population dynamics. Moreover, there is no doubt that it is quite normal that the harvesting term involves delays. So to create a more realistic model and to incorporate the minimum amount of essential biological information about it, we took into account the harvesting strategy, which is modeled by an iterative function that incorporates implicitly the time and state dependent delay, describing the maturational phase before the blood cells are released into circulation. The production term incorporates this same delay that gives rise to the appearance of the second iterate in equation 1 and another time varying lag, which represents the transit time required to release mature white blood cells into the circulating bloodstream. Let's turn now to the core of the work, where I will state and prove our main results. The key task of this part is to find some sufficient conditions that ensure the existence, uniqueness, and continuous dependence of positive periodic solutions of equation 1. For tackling this last one, we will use an efficient technique based on Banach and Childers fixed point theorems, as well as the Green's functions method. So let's get started. Let capital X be the Banach space of all T-periodic and continuous functions equipped with the supremum norm, and omega is a convex, closed, and bounded subset of it. For its exposition, we introduce the following notation, and throughout this work, we need these 5 assumptions and this lemma. Lemma 2 guarantees the equivalence between our equation with the periodic boundary conditions and the following integral equation, where the kernel is a Green's function given by expression 9 and sandwiched between these 2 values. Moreover, it suffices estimate 11. Now, for lemma 2, we define an operator A as follows. And thanks to this lemma, fixed points of A are solutions of equation 1 and vice versa. So, for reaching our desired results, we proceed in 4 steps. We prove that A is well defined, A maps omega into itself, omega is compact, and finally, A is continuous. By the periodic properties, we can prove that A is well defined. And thanks to condition 4, operator A is continuous. For proving that A is continuous, we take into account the fact that 1 plus the second iterate is strictly greatest than 1 for getting this estimate. And by using the Lipschitz condition 4 and the Green's function property 10, we obtain estimate 14 and 15. Now from lemma 1, we obtain estimate 16, which proves that A is Lipschitz continuous and hence continuous. On the other hand, lemma 5, by the aid of Green's function properties 10 and 11, gives conditions under which we can prove this inclusion. Now we are ready to state and prove our first theorem. If condition 3 to 7 hold, then equation 1 has at least 1 positive periodic solution in omega. The first step of the proof is based on using Ascoli-Arzilla theorem set omega. Indeed, by the definition of omega, omega is a set of bounded functions that are bounded by the same constants. Moreover, it is a set of Lipschitz functions with the same Lipschitz constant. And as a consequence of lemmas 3, 4, and 5, A is well defined, continuous, and maps omega into itself. So all conditions of Childers fixed point theorem are fulfilled. Hence, A has at least 1 fixed point in omega, which means that equation 1 has at least 1 positive periodic solution. Now, For the existence and uniqueness result, besides the hypothesis of theorem 1, we suppose further that estimate 17 is satisfied. Then equation 1 has one and only one positive periodic solution. From the proof of lemma 4 and the additional condition 17, the operator A is a contraction. So by virtue of Banach contraction principle, we deduce that A has a fixed point X, which means that is the unique solution of equation 1. Under the same assumptions, the unique solution of equation 1 depends continuously on parameters. Now, we provide the two examples to illustrate the correctness of our main findings. In the first example, we consider the following delay hematopoiesis model, where the period equals 8 days. So we arrive at this estimate where the additional condition 17 in theorem 2 is satisfied. Thereby, we conclude by theorems 2 and 3 that the equation 18 has a unique positive periodic solution that depends continuously on the harvesting term H. The next example demonstrates the real power of theorem 1, which guarantees the existence of at least one solution, even when Banach fixed point theorem cannot be used. Consider the following delay hematopoiesis model with the period of equals 10 days. We arrive at these estimates, and unfortunately, the additional condition in theorem 2 is not satisfied. Thereby, Banach fixed point theorem cannot be applied here, whilst all conditions of theorem 1 are satisfied, which proves that equation 19 admits at least one solution in omega, which is not necessarily unique. So that brings me to the end of my talk, which is devoted to study the delay hematopoiesis model with the iterative production and harvesting terms. The main idea here consists to transform our problem into a fixed point one by pursuing the following path. First of all, we constructed a Banach space, an appropriate Banach space, and a suitable subset of it for making the iterative terms were defined and applying the chosen fixed point theorem. The next step is the conversion of our problem into an equivalent integral equation. And from this last one, and by the help of Arzelà-Scylla theorem, some functional analysis tools, and some useful properties of an obtained Green's kernel, we succeeded in defining a continuous integral operator from a compact set into itself. Next, we concluded by the shortest fixed point theorem that A has at least one fixed point in omega, and therefore equation 1 has at least one positive periodic solution in omega. For the existence and uniqueness of solutions, it was wise to use Banach fixed point theorem for establishing such result. Here are our main references, and thank you for your attention.
Okay, thank you very much. What questions do you have? It's very interesting talk and a very nice presentation. Thank you.
Thank you.
And what questions do you have, dear colleagues?
Okay, so I have one question. So this thing really catches my eye that you use in your model function x, where you put another x in it. It's x squared by the square in square brackets. Can you show this again?
Please.
Yeah, I don't understand. Please, what do you say?
No, your model show us.
Yeah.
Oh, again.
What about our model?
Show it again, please.
Show it again. Yeah.
No, and yeah, what? Yeah. So we use x.
Yeah.
Yeah. There is x squared, kind of squared.
Yeah.
When we put x instead of x. Yeah. So this thing catch my eye. It kind of messes my head because it's this x is dependent on time, but you put inside x, so it's kind of physically messed up with my head. And I have another question. So x is unknown function. We can use it. So we draw it. Yeah.
Yeah. The composition of x with itself.
Yeah. Function of itself. Yeah. And we kind of this thing kind of goes like something. But what if x is too large, and we kind of jump into the far future when we don't know how x will behave?
This term results from the fact that there is an implicit delay x t minus tau, and tau equals t minus t x.
Implicit delay. So there cannot be such cases when, for example, so time is for example 1. We go from 0 to 1, but x is too large. X is like 3000, and we must to put 3000 into the x, but we don't know yet how much of x will be in the point of 3000.
This I don't understand what you mean, but here x is bounded. For this,
okay. So
the iterate. I don't understand what.
Okay. He understood that if x is bounded,
and therefore time is also bounded.
The composition is well defined.
Yes. And so if x is bounded function, that
because there can be caveats in such form, I think.
Okay.
Okay. So thank you.
Thank you very much. Other questions, please.
Omega is the subset of bounded sets like
Okay.
Rho and M.
And no, so time is bounded, but it's not a big issue, I suppose.
And the Lipschitz condition.
Okay.
Function.
Yes. Thank you very much. We understood everything. Thank you once more. And let me. Okay, thank you. Let's thank our speaker.